Korean math is weird. And I don't mean that Korean students are learning some secret alien math that the rest of the world doesn't know about. It's not like the curriculum is teaching dramatically more advanced concepts than an American high school. Okay, the pacing is faster usually, but the actual topics, algebra, functions, geometry, trigonometry, basic calculus, a lot of it overlaps with what students everywhere are learning. But here's where things get scary. The testing complexity is on a completely different level. A Korean student might learn the same general concept as an American student, but then the test questions look like it was written by a math professor, a puzzle designer, and a villain working together in a basement. So here's a problem from an official practice test for the Sunung, which is the Korean SAT. By the way, if you don't like listening to math problem walkthroughs and just want to hear the gist of what I want to say, feel free to skip over to this time. We're given two graphs, y equals 2 to the x power and y equals negative 2x squared plus 2. These two graphs intersect at 2 points, x1, y1 and x2, y2, where x1 is smaller than x2. And we need to determine which of the following statements are true. A, x2 is greater than 1 over 2. B, y2 minus y1 is smaller than x2 minus x1. And C, square root of 2 over 2 is smaller than y1 times y2, which is in turn smaller than 1. Feel free to pause and give it a go. Now here's the solution. Let's call y equals 2 to the x power our function f of x, and y equals negative 2x squared plus 2 our function g of x. So first, let's draw both graphs with their important intercepts. If you know the basic shapes of exponential and quadratic graphs, you can sketch this by hand. I would go over all the details, but that will make this walkthrough way too long, and that's not really the main point of this video, so maybe I'll save that for another time. But anyway, statement A asks whether x2 is greater than 1 over 2. When we plug in x equals 1 over 2, we get square root of 2 for f of x, while g of x gives us 3 over 2. Since 3 over 2 is greater than square root of 2, the quadratic graph is still above the exponential graph at x equals 1 over 2. That means the second intersection point, x2, must happen after 1 over 2. So statement A is true. Now statement B asks whether y2 minus y1 is smaller than x2 minus x1. If we divide both sides by x2 minus x1, we get the slope between the two intersection points. And since x2 minus x1 is positive, the inequality direction does not change. So the question becomes, is the slope of the line connecting x1, y1 and x2, y2 less than 1? This part is a little tricky. Look at the point where f of x crosses the y-axis. That point is 0, 1. Let's call this point alpha. Then look at the point on G when x equals 1 over 2. We determined early on that this is 1 over 2, 3 over 2. Let's call this point beta. Now the line from alpha to beta has a slope of 1 because the rise is 1 over 2 and the run is 1 over 2. But more importantly, from the graph, we can compare this line with the line connecting the two intersection points. Graphically, the line through the two intersection points is less steep than the reference line we are using, so its slope is less than 1. That means y2 minus y1 over x2 minus x1 is less than 1, which means y2 minus y1 is less than x2 minus x1. So statement B is also true. Finally, statement C asks whether square root of 2 over 2 is smaller than y1 times y2, which in turn is smaller than 1. Since the two intersection points are on the exponential graph, we know that y1 is equal to 2 to the x1 power and y2 equals 2 to the x2 power. So y1 times y2 would equal 2 to the x1 power times 2 to the x2 power, which would mean 2 to the x1 plus x2 power. Now we just need to estimate x1 plus x2. The quadratic graph G is symmetric about the y-axis. So take the point x1, y1 and reflect it across the y-axis. Let's call that reflected point gamma. The x-coordinate of gamma is negative x1. We know that x2 is greater than 1 over 2. We also know that the x value here is 1 because when we solve for the roots of g of x, it's 1 on the positive side. Then this length, which can be expressed as negative x1 minus x2, has to be shorter than this length, which is 1 over 2. So we get 0 is less than negative x1 minus x2 is less than 1 over 2. Multiplying everything by negative 1, the inequality flips. Now use base 2. And since 2 to the negative 1 over 2 power is square root of 2 over 2, we get square root of 2 over 2 is less than y1 times y2, which is less than 1. So statement C is true as well. So the answer is all three statements are true. So how was that? Easy? But the best part about this problem is that even though it's close, this isn't even considered one of the so-called killer problems on the Korean SAT. Killer problems are the hardest problem on the Sunung, infamous for their almost Olympiad-like difficulty. They often combine 3 or 4 different areas of math into one question, and they're basically designed to separate the wheat from the chaff, or more realistically, the top 1% from the top 5%. In a lot of Western math education, there's a strong push to connect math to real life. Here's how this applies to economics. Here's how this applies to data. Here's how this applies to construction. But Korean math often leans much more toward pure analytical problem solving and reasoning. So why is it like this? My take is that Korean math is hard because the system needs it to be that way. Korean schools rely heavily on relative grading or 상대평가. Students aren't just being evaluated on whether they understand the material, they're being ranked against each other. And when admissions are this competitive, the system needs tiny differences in score to become meaningful. If too many students can ace the test is useless for ranking. So the questions become harder and harder and harder, not because that's the best way to teach math, but because it's an efficient way to separate the top 1% from the top 5%. So naturally, when the goal is to differentiate students' mathematical performance, the focus shifts away from let's show students how this math is used in real life and more towards let's make problems that are hard enough to rank people very precisely, even if the math is only remotely connected to real life. You can only imagine the potential problems to this kind of approach to math. Think of a piano analogy. The concert is coming. So you get 2 types of kids. The first type makes it. They become proficient. They look impressive. But they might not actually know the depth behind what they're playing. They mastered the piece, but they didn't have the time to love the piece. And then there's the second type. They look at the pressure and the stress and they just say, yeah, no, I hate piano. And they quit. I think Korean math is quite like that. Students become technically strong. They solve problem after problem. They learn how to recognize what kind of monster is hiding inside each question. Now, I'm not saying practice is bad. Practice is necessary. You don't become good at math by just staring at beautiful explanations and saying, wow, so deep. You have to solve the problems. But I wonder if you take it too far. There's a whole side of math that students rarely get to experience in Korea. How concepts connect, why they were invented, how a formula isn't just a thing to memorize but the result of someone trying to understand the world more clearly. In Korean math, all of those things feel like luxury items. If you try to talk about this to the Korean education system, the system says, hey Mr. Math Lalaland, get your feet back on the ground. We have a test to prepare for, and this test can decide the course of your future. Is that bad? It's complicated. I don't think you can just say, oh, Korean math is bad and Western math is good. That's too simple. The Korean system produces students with incredible discipline and analytical power. If you want to major in engineering or physics, that training is a superpower. There is a real value there. But I think we lose a lot of perspective. We lose the chance to see the beauty behind the ideas. We lose the chance to actually enjoy what we are doing. Because when you really understand and appreciate what you're doing, even hard work feels meaningful. It feels like you're part of a long human story of trying to understand structure and logic. But if math is only ever experienced as a race, a ranking system, a filter, then even the most beautiful ideas can start to feel like weapons. And that to me is the tragedy of Korean math, or at least tragedy with a question mark. Because the system is impressive and powerful, but it makes so many students walk away thinking they hate math, when maybe under different circumstances, they could have loved it. Maybe the problem isn't that the math is hard. Maybe it's that we aren't giving students enough time to understand why the hard things are worth loving.